Okay, hello everyone, and thanks to Helen and Stephen for inviting me along to talk about this. Yeah, as Mark just gave a quite detailed overview of the technology behind the Maia Mapper and how we can really maximize the data output from some of our samples. I just want to go through some of the kinds of study that we can get from that. And where it can lead us to. Helen asked me to discuss a particular project that we recently completed with OzQuest and South 32, where the outcome of that was actually negative for the company in terms of they didn't find something that was economic, but it was positive looking forward because it saved them lots of potential exploration funds further down the line. They were able to make a decision on this project far earlier than they otherwise would have been able to. And really to demonstrate why this didn't work, I want to use a very specific example of a sediment-hosted zinc-lead system that does work because it's one of the largest in the world. So I'll go through that step by step. So we were working on the Blue Billy sediment-hosted zinc project in West Australia. This is a black shale unit that occurs within the Banjmal supergroup between the Pilbara and the Yilgarn cratons. The company were targeting specifically an HYC or MacArthur River style sediment-hosted zinc-lead deposit. A few reasons for that. This unit is the same age, more or less, as the Barney Creek Formation that hosts the HYC deposit. It's proximal to, well, certainly the project area was proximal to a major fault and hosts black carboniferous shales. There's a disclaimer there. And also some legacy drill cores from the 80s had intersected modest grades of zinc around 1 to 2%. So from an exploration point of view, it looked quite nice. So this is, I'll go through this quickly. This is a basic overview of the geology. So we have, this is the Banjmal supergroup here, separated into the Edmund and Collier groups from the early Mesoproterozoic through to the probably the early Neoproterozoic. And the Blue Billy Formation sits, it's a black shale dominated unit, it sits just in here within depositional package 2. This is where the project sits, so it's just on the northern boundary of the basin with the older Ashburton group. And initially we were working on 4 diamond holes that were freshly drilled in 2017. But were subsequently added to with 13 RC holes later that season, plus a number of legacy holes that I'd been working on some years earlier. The project is actually associated with some of the highest surface zinc geochemical anomalies in all of the state. And some of the reprocessing work that we've been doing over the last few years of the GSWA open file surface geochemical database, which had some real batch effect overlaps. The exercise we went through to normalize that as best we could, this area still came out on top with, in some cases, almost 1,000 ppm zinc. So it looked interesting. When it was drilled, we did some downhole geochemistry just through conventional assay methods. This is the breakdown of the stratigraphy that was intersected, and it might be difficult to see on this screen, but we're getting up to kind of low percent zinc along this this target horizon, which is a maximum flooding surface black shale intersection within the Blue Billy Formation, and this is what it looks like in core here. So we have over tens of kilometers, we have this consistent zinc anomaly in these black shales, specifically in the maximum flooding surface. In the carbonates down here in the Irigoli Formation, there's some quite enhanced manganese enrichment, which I'll go through in a moment. But all of these together led us to explore some key questions. So we wanted to map out and characterize the zinc mineralization at the Bluebilly project. We wanted to have a look at the manganese enrichment and explore if those were linked to a sediment-hosted mineral system as far as we knew it. And other similarities to some of the other large sediment-hosted deposits, such as trace element enrichment with things like germanium and thallium. I'll just jump straight to the conclusions before I show you the data. This isn't a prospective mineral system with similarities to HYC, and these are why. The fault that is proximal to the project wasn't actually active at all, we think, during sedimentation. It kicked off later. And as far as we're aware from other sediment-hosted zinc systems, that's a requirement, although I would argue that. But the zinc mineralization has been overprinted quite extensively by chlorite and pyrite alteration. The manganese enrichment reflects manganese-rich chlorite amphibole alteration rather than the types of manganese enrichment we see at HYC and heaps of other things. But let's explore how the Maia Mapper really got us to those conclusions. So to understand this, we have to first understand what one of these massive or supergiant sediment-hosted zinc systems looks like HYC. So this is the HYC pit as of 2016, I think it was. This is the ore zone through here. On top of that, we have multiple layers of talus breccia. So these are sedimentary breccias that come off a fault scarp. And then sitting on top of that, we have a anomalously thick black bituminous shale that sits on top of it all. And I say it's anomalous because that black shale doesn't actually occur anywhere else in the Barney Creek Formation throughout the basin. This is what the ore looks like from the Maia mapping. So in the central part of the sub-basin, which forms the deposit, the mineralization's characterized by this finely laminated zinc ore. So this is another RGB map from the Maia Mapper, and zinc is in green here. And in this map, that's all you really need to look at because it's all that's really is there. There's hardly any carbonate left in this sample and just a few little bits of pyrite. Out on the fringes of the deposit, you move into a nodular carbonate facies, which is what we see here. So this is a soft sediment slump of interbedded pyrite with organic-rich mud, and between that is some nodular blebby carbonate. And with the same color scheme, you can see that the zinc mineralization here is exclusively associated with dissolution around the carbonate nodules. So what does the mineralization at Bluebilly look like? Well, it looks similar to the HYC stuff in as much as it's locally bedded. But if we keep going in through the scales, we can see that this bedded zinc is it's being affected quite a lot by some late stage remobilization processes. So these are again the same color scheme. We have these chlorite and pyrite veins that are coming through with some carbonate through there as well. It's not really resolved in this map. When we look at this further up close, in this case, it actually does look quite similar. We have sphalerite that's growing around earlier pyrite. So if you just took this sample as a type example of the mineral system, you'd think actually it's not too dissimilar to what we see at HYC. But if we start looking at some other samples, this is the importance of having diverse data sets. This doesn't really come out on this screen too well. This is a lower grade sample through here, kind of few thousand ppm probably. You can see that there is bedded laminated sphalerite in here, But when we get really into the guts of it, we can see that sphalerite is being replaced by pyrite and by chlorite, and this is something that we see quite representatively throughout the sequence. When we did some spot analysis on these, we can see that the chlorite's actually really poor in zinc, but the sphalerite's obviously where the zinc is. So we reckon that that's probably well, I can go into that later rather than dwelling on this too much, because I've got lots to show you. Right, so manganese deportment. Here's our trusty old sample, the slumped pyrite carbonate. This is a different color scheme through here. So we have zinc in red, manganese in blue, and calcium in green. And what we can see at this scale is that where the green blues are in the carbonate nodules, there's actually manganese present in all of the carbonate, and that reflects to me as a geochemist that there's incorporation of manganese 2+ into the carbonates in an anoxic diagenetic or depositional environment. What's interesting though is where these real dark blues and purples come in, and that's where there's enrichment in manganese proximal to zinc mineralization. If we start going in with some of our more targeted techniques, so in this case EBSD, if we focus on the bottom image here, we can see that the localized manganese enrichment occurs around dolomite nodules as a thin manganiferous rim, which occurs spatially proximal to this sphalerite mineralization. Sphalerite doesn't respond well to this analysis, it wasn't polishing up too well. That's why we weren't able to map it. It's crystal orientation with that. So that's what manganese deportment looks like at HYC, and that's what we think the manganese enrichments in that mineral system really represent. If we look at the manganese enrichments at Blue Billy, for example, in the upper part of the stratigraphy, and then we've done some of the wavelet tessellation exercises that Mark described a minute ago here, we can see that calcium, magnesium and manganese follow quite nicely in the upper carbonate sequence, so that's quite consistent with a manganoan dolomite. But down here, they're actually not too close. So we've got these big manganese enrichments in the lower part of the stratigraphy. So one of our jobs was to really explore what that represented. When you look at the textures of these rocks, just in core, they just look like these soft sediment slumped siltstone carbonate sequences such as this. But this was grading quite high with manganese. But when we ran the sample through the Maia Mapper, we can see this really distinctive zonation of what have we got here? It's too far away. I think that's iron, manganese, calcium through here. So the purples and blues through here, they actually represent manganese-rich chlorite alteration through here. And what's the... Oh yeah, so there's really low-level zinc down here. Just added that for comparison. But when we look through this this zone through here with some more micro characterization techniques, we can start to pick out the mineralogical complexity of this alteration zone, and we can see that there's this gradational alteration throughout the zone where we have chlorite and amphibole, which really is not very similar to what we see at HYC. And this is actually quite a common theme throughout this basal part, where we see these zoned areas of manganese-rich chlorite, which texturally within a sedimentary rock that's been subject to soft sediment deformation, it's infinitely complex to try and pull this apart. So being able to just see these broad-scale element variations on the drill core scale, it helps refine our understanding of things quite easily. If we were to just take a thin section through this, because it looked interesting or the geochemistry was interesting, I have no idea where you would end up, because it would be such a subjective thing to choose here versus here, and you would get a different result every time. In the upper part of the sequence, though, we can see that there's just mass correlation between the manganese and the stratiform carbonates, and I'm fairly happy that that's incorporation of manganese into the carbonate crystal structure due to the paleo redox sequences. So what the Maia Mappers really helped us do is understand that in the basal part of the stratigraphy in this project area there was quite a unique but quite a clear alteration signature, which helps us understand how things evolved. If we look at the trace elements between the Bluebilly formation, which is the host of the Bluebilly project, versus the Barney Creek formation, I would usually apologise for putting up geochemical plots at a conference, but this conference has geochemistry in the title, so sorry, not sorry. The sediment-hosted zinc deposits globally have been attributed with large thallium anomalies for some time. That's nothing new. My new favourite element is germanium in this case. I've been doing a lot of work with that in recent weeks. So I just wanted to use these two as a bit of a comparison. So this is from 561 odd samples in the Barney Creek formation, plus some stuff from HYC itself. We can see that thallium versus zinc, we're getting around the 1 to 2 ppm over 100 ppm zinc, whereas this is where you end up with the deposit, and you're not too far away with the background Bluebilly formation. The same can be said for germanium, which is an increasingly, I think, important pathfinder for sediment-hosted zinc systems. You've got about 0.1 ppm germanium in the bulk of the Barney Creek formation, over 100 ppm zinc, and the similar-ish but slightly elevated background in the Bluebilly formation. What I will say is, though, that the majority of these samples come from stratigraphy proximal to the project area. So just going straight to it, we couldn't resolve germanium and thallium very well in the Bluebilly formation. It's just too low. We'd probably have to go on to much higher dwell times and do more work for it, but we didn't think it was worthwhile. But while we're here, I just thought I'd show you what the Maia Mapper can do for both elements from deposits such as HYC. So we have two separate samples here. This one looks like this in section, this one looks like this. We've seen this one already before. It's quite a nice sample. This is a germanium calcium zinc map down here. So it looks like a little bit further close, and you can see there's a close correlation with the zinc and the germanium, and we think that that's germanium sitting quite nicely within the sphalerite. If we look at thallium in the same sample, sorry, in the other sample, you can see that thallium sits specifically within pyrite, but is very highly concentrated within this band through here, and we would never have picked that up. It's very difficult to resolve thallium based on peak overlaps with things like lead and sulfur, but we're able to pick this out with the Maia Mapper. And typically thallium only ever occurs in very low concentrations. We just so happen to have a very good case example here where thallium occurs in the hundreds of ppm, and we're able to map that out and add this to our story. So if we pick that area of high thallium enrichment, and here's an EBSD map of the area I showed you before, we can zoom into some areas such as this, do some traditional SEM microcharacterization, and we can see that the pyrites are comprised of rounded probable framboids that have been added to by multiple zones of pyrite overgrowths. We coupled some really good micro or nano characterization techniques, such as the focused ion beam TOF SIMS with Will at John DeLater. He might speak about that later. And we can see in this example here that thallium is very much enriched in the overgrowths of the pyrite, and that's actually added quite a lot to our understanding of that, and that's in a paper that's in review in economic geology right now. So just some takeaways. The Maia Mapper has some huge potential for us to get a better understanding of certain aspects of mineral systems that we hadn't even thought of before. The mapping of trace elements at the micro scale, but on macro samples, is really an eye opener for us, and will lead to quantum shift in the way that we approach this. And that's all I wanted to discuss with you today. Thank you.